So the place where we left off last time is that we'd actually done constant propagation, where we actually defined the lattice and defined the analysis, and then we realized that the lattice was infinitely tall, and so we redesigned our lattice in a slightly different way, where we basically had every variable mapped to some piece of information, and that information is either top, a constant, or bottom. And in that way, we're able to basically re-express our flow function for this operator, and kind of maybe what you would think as a maybe slightly more intuitive way of thinking about it. But in general, there's kind of this idea of designing your domain. And a lot of times, the power set lattice is fine, but in some cases, it's actually easier to represent it in a slightly different way. So, okay. So what I want to touch upon today is, first I want to talk about this may versus must. We've used the word may and must here and there, and I want to just talk a little bit more about that. And then after that, we're going to try 2 more examples of data flow analyses. So you guys are going to try out your hand at this. We're going to do something called available expressions, which is going to be useful because getting practical with these things is good for the midterm. So the midterm is a week from today. So it's on Tuesday, a week from today. And basically the midterm is just, you're going to write an analysis. It's basically more or less define the domain and write the flow function. That's all it's going to be. And then show the analysis running on an example. Right? So it's the kind of thing we've done several times in class, and I'll have you guys try it out a little bit to get a feeling for it. And then after that example, which you guys are going to try out, we're going to do an analysis that's very different because all this time, this whole time, we talk about forward analyses. It turns out that there's also backward analyses, and we'll get to that later today, or possibly on Thursday. So, okay, so let's talk about may versus must. So we've kind of used the words may and must kind of here and there, and it turns out that there's this big distinction between may analyses and must analyses, and it's a very confusing thing. It's not like there's universal rules that will always apply, but there's kind of this intuition that does apply often, so we want to talk about it. So just as an example, let's say that we compute a whole bunch of points to pairs. So a set of points to pairs. So as an example, something of the following form. Suppose that we compute some information. Something like, A points to B, and then B points to C, right? So that's a pair of information, right? That's a set, and we'll be considering an analysis that computes these kinds of sets. Okay? So if we say the interpretation of this analysis is that what it's doing is it's computing must point to information, what does this mean? Right? What does it mean that we've computed this set? It means that A must point to B and B must point to C. In other words, is that if we compute a set of the form, something of the form X, or Y, then it means that during program execution, no matter what path you take, at that point where you computed that, X must point to Y. Does that make sense? So basically what it means is that if I have a control flow graph, let's say I'm going to draw a control flow graph here. This is a control flow graph. And there's an edge right here in this control flow graph. And if the computed information at that edge in the control flow graph is this set, then what that means, and it's a must point to analysis, it means that on any program execution, when you reach this point, if you look up the value of A, it'll be equal to the address of B. And if you look up the value of B, it'll be equal to the address of C. On any execution of the program you get here, you will know that A is equal to the address of B and B is equal to the address of C. Right? Does that make sense? So that's the interpretation of a must point to analysis. Now so let's say that this is a may point to analysis. So let's say that we actually compute some may point to information. So what is the meaning of that? See, must point to is pretty straightforward. It's intuitively, it's like, okay, this thing must point to this other thing. I mean, you're computing it, and it's straightforward. But what about may point? It's kind of a weird thing, right? Yeah.
There's like two interpretations. One of them is it's a complete set of things that make sense, and one of them is some subset of things that make sense.
But that's really, wait. I'm very confused because so the problem with this, that what you're saying is, if I heard correctly, you're trying to define what may point to means, and then you use the word might point to. Right? In your definition, you say, oh, it's either. I guess you said.
So it has to be the complete set, doesn't it?
The complete set of the things that it may point to. But then, what do you see what I'm saying? That's the thing. What does it mean, the complete set? So it's actually confusing, right? I mean, how do we actually define that? Yeah.
We don't know exactly where it's pointing, but we know for sure where it doesn't.
Okay, so that's an insightful observation, which we'll get to in a second. So let me restate the observation that you're making. So let's suppose that the information we're computing is something like this. So what you're saying is that if this is a may point to information, it says that A may point to B and A may point to C, and you don't know which one it is. But what you're saying is, what this should tell you is that it should tell you that that A does not point to anything else, right? So sometimes it's telling you that it can only point to B or C, but nothing other than that. So sometimes there's this, I think I see what you're saying, there's a sense of completeness that it should cover all the things that it may point to, but nothing more, right? That did nothing, yeah, so, yeah.
Are we considering the empty set of may point to as saying it can point to anything, like we don't know what it might point to, or are we saying it points to nothing?
Wait, what? You're saying what is the empty set?
What would that imply if may point to A and returns empty set? Does that mean we don't have any information on what it may point to, or is that saying it cannot point to anything?
It's saying, well, that's a good question.
Well, that would help define it, right? That's what you're...
So, well, right, so if I say that, right, well, I mean, this is, part of it is for us, right, so what do you think it should be? If it's returning the empty set, and it's a may point to analysis.
It's not a pointer, maybe?
Yeah, I mean, it's not pointing, it's really, that it doesn't point to anything. It's not pointing to anything, right? I mean, for example, it's an integer, or a string, right? Something that will not point to anything. Or it's null. I mean, although null is a bit confusing.
So a default case here for a pointer, where we have an initializer, for example, would be like A points to star.
So, wait, say again?
If in C, for example, I say integer pointer A, and then semicolon.
Right.
A points to star at that point.
Well, right, I mean, there's a question of where, right, well, okay, so...
Before I initialize what it points to, I have no clue what it may or may not point to.
Right.
So, that's why I'm asking like default.
Right, so that's, I mean, I think usually when you start with something like that, you basically initialize everything to the bottom, except for the beginning, which is top. Now, in this case, if you got to initialize, right, so the question, so this is part of the question, so what's bottom and what's top, and may versus must are actually different things. So for example, if you actually, let's start with the may point to analysis. If I basically ask you, like, what's like the clearest, easiest way to just return an answer for that?
All the variables.
What?
All the variables.
All the variables. I mean, that's what I mean, like all the variables. So you just put everything in there, and basically, and that's your most conservative thing, and that basically means that it's all the things. Now, if it's uninitialized, you can actually put it to, so the other opposite extreme is the empty set. And the empty set basically says it points to nothing. right? And sometimes if it's an uninitialized variable, you can actually, and you could make, so the answer that's always, that you can immediately return is what? It's top, right? Top is the most conservative thing. You could just always like back, it's like the simple, you can always back to bottom. Go back to bottom. Oh, that sounds funny. No, but the point is that that's your backup plan. And so in this case, the backup plan is the full set. The most precise answer is the empty set. And if you don't have the exception that's not initialized, you can basically put it to the empty set. Okay? So an uninitialized variable, let me know this kind of quick.
But it will be reiterated.
Eventually, yeah, of course, eventually once you assign something. Now, here's the thing. An uninitialized variable, you started off as the empty set. But what about a parameter that comes in? Your function. Let's say you have a function and there's a parameter coming in. See, that is different. What do you assume? What are you going to assume for that? For that, you should assume the full set, because you have no clue what the same point is, right?
And you don't want to report it as unreachable or something at all.
Right, because it's exactly, yeah. But if we go back to this thing, so how are we going to, so how do we talk about this? So it turns out that there's a way to formalize this, and it's basically very kind of nifty. We can actually do it the other way around. So basically, if during program execution, if we compute this, then during program execution you have to have this. Here, basically just flip it around, and you say, if during execution it's possible for X to point to Y, then we have to have X, our Y in our set. And what that means is we can compute more than what's there. We can always put more things. So it's always safe for us to basically compute the full set. As long as we have the things that do characterize what's happening at runtime. So here, what the make pointer analysis allows us to do is allows us to capture what's there at execution, and it allows us to over-approximate, to basically have more things there. Whereas this one, basically, if you compute it, then it has to be X points to Y during program execution. Yeah?
Is there any way to differentiate the notation if we're looking at must point to or may point to?
No, that you have to define. So that's part of the definition of the analysis that you have to define. You have to say, this is the analysis I'm writing. I'm writing a must point to or a may point to. You have to decide if it's what kind of analysis it is. Is it a may analysis or a must analysis?
So initially, you can't have must point to in an analysis with may point to.
Well, you could write analysis that compute both information. In this case, in this case actually, as actually was pointed out, there are correlations between must and may. For example, if we have may point to information, basically whatever is not in this may point to set is the must not point to, right? So basically, if you have a whole bunch of may point to information, the thing that's not in there are things that X does not point to. For sure, you know for sure that X does not point to. For example, here, if we have another variable, say D, there's another variable D. Here we know that A does not, if this is your may point to set, then you basically can learn the must point to fact that A does not point to D. And in fact, you can write an analysis that basically computes the must not point to fact. It's a must not, point to fact, and you can, store it as, again, pairs of things, but the interpretation there is not that A may point to D, it's that A does not point to D. And once you know this, you know for sure that it does not point to D.
I remember, it's pretty when we talked about unreachable code, when we had a set that had maybe a may point to set where A could be one thing and it could be another. And then that's how we use unreachable code. But there's no way to tell if may to or must point to set, and you get quite confused with that.
Yeah, so that's why you have to be really clear to say what kind of analysis you're doing. And if you really want, you can always add more notation to basically say this is, you can basically add special arrows. Basically, this is the may point to arrow, and the must point to arrow is like a double arrow or something like that, right? That basically says this is must point to. So you can always differentiate them, but usually the context in which you're writing your analysis, you're going to say, this is the analysis we're going to define. Now, of course, in an implementation, you will, of course, have to distinguish these, because if you have both analyses running in parallel at the same time, you'll have to basically give them different names or different kind of pieces of information. Yeah?
Couldn't we just use one set to piggyback off of the must if we use that?
Yeah, there are ways of doing it, but you have to be careful because there's null. So if you include null properly, so there's also null. So if you line where you have null, you have to kind of be careful with that. Because, yeah, see, I mean, for must and may point to, there are tricks that you can play like that. But in general, that's not the case. I mean, in general, there's always usually a may version of the problem and a must version of the problem. So, I mean, in this case, it's just that at runtime, there's only a finite set of things you can point to. And so what you're saying is, if in your may point to set there's only one thing,
And
then you could say,
no, it's non, I mean, you might want to know may point, a must point to null could be useful, but it's not star, basically.
right. So if you encode null properly, then you would actually get that kind of information. That's true.
And then you only have one set that you're passing around.
Right, but that doesn't. But there are. Right, but the point is that these two analyses actually have also different merge functions. So actually, I think there are cases where if you do your man analysis in this way, you can actually lose precision when you because of the merge points. That you would actually not lose precision if you had a specific must point to analysis. But the broader point here is that there's two kinds of information. There's the kind of, and so it's actually really important to understand that there's always this kind of, oftentimes we have to talk about may versus must. And why? So why is that fundamentally there's two versions of this problem? Okay, the reason, actually there's a third version of the problem. Okay, there's a third version, which is, let's compute exactly the set of things that X points to at runtime. Okay, that's undecidable, right? This is the problem. The problem is computing the exact answer of what things X would actually really point to is undecidable, because there's basically it's equivalent to the halting problem, right? You're trying to compute non-trivial information about a program, and so that's why there's always two versions of the problem in terms of how you allow yourself approximation. So what this allows you to do is this allows you to compute the real set, but also add more information. Basically, just keep on. You're always allowed to add more information, and this is what makes it decidable. That we're not saying compute exactly what X is going to point to. You're saying compute what X is going to point to, and possibly more things too. Right? But definitely don't compute less things. You see, in a may point to analysis, you have to compute all the things that X may point to, and possibly more, but you're not allowed to forget things that X could really point to at runtime. Whereas the must point to information is the other way around. You basically want to compute the exact answer or less than that answer. Right? So in the must point to, it's always safe to return the empty set. The empty set is always safe. Right? Because then it's like, what's the thing that must hold? If you say none of these facts hold, right, the only obligation you have is if you compute something, then it better be the case that fact is correct. But it's always safe to just go up your hand and say, I compute nothing. So the empty set is always okay in a must point to analysis. Whereas in a may point to analysis, the full set is always okay. Does that make sense? You see how there's these two, basically you have the exact answer, the precise answer, which we'll never be able to compute always because it's undecidable. And then there's two ways of approximating it. One allows us to basically return subsets of this, and the other one allows us to return supersets.
Or must point to them, is that a situation where you want to try to work down? Or
No. So the way it works is we always initialize everything at bottom and go from bottom.
Flip it.
But the lattice gets flipped. Right? So this is where the lattice gets flipped. So if we look at a power set lattice, okay, where you have sets of facts, if we look at this, so and you want to order your lattice, right? So if we look at most conservative top, that's the answer that's always safe. So what's the answer that's always safe in a must point to in a must analysis?
Empty.
It's always the empty set, right? So basically, a must analysis, the only thing you have to do is guarantee that as soon as you put something in there, it has to hold. But if you return the empty set, there's no obligation on your side, right? The only thing you have to guarantee is that whenever you got to be careful, everything you put in there, you got to make sure that you're absolutely sure that it's correct. So it allows you to approximate by just always returning things that are less than that. What about the most conservative for a May analysis? It's a full set, right? You just return everything. You're like, okay, everything. All facts. I just give up.
Full set will contain all the variables plus 5.
Plus what?
Plus 5. Union 5.
You mean the empty set? No, I mean,
Because I think the pointer being not initialized and pointer being initialized to null are two different cases.
Sure. So, I mean, right, absolutely. So, I mean, the way you model that, you'll just have a special null variable.
Okay.
You would introduce a special variable called null, and whenever you do x equals null, you just have x point to null. That's the best way to handle null.
And that is the same as this 5, right?
No, this is the empty set, and this basically represents in a must. Wait, you're talking about a must or a May analysis? Yeah, sorry, we're right now in a wait. Hold on. So in a must analysis, the most conservative answer is just to return nothing. So, but not just for May pointer. For example, the constant propagation was the same thing, right? Constant propagation, we always could return the empty set, no constant, nothing. Right? You can always, that's the most conservative answer. And so, but here, this full set is just a full set of all the facts. Basically, you just return them all. You're like, I don't know which one's hold and which one's not. They may all hold. I'm just like, I give them all out. Because basically what happens is, in a must analysis, every time you state something, you have to be sure that it's correct. Whereas in the May analysis, the worry is you're not allowed to forget things. Right? Does that make sense? I mean, you're not allowed to forget things. So here, to be conservative, you have to return everything because you're afraid of forgetting it. And you're like, here's everything. Whereas in the must analysis, if you can't know anything for sure, so you just return it with the empty set. And what about, okay, so in the must analysis, the most optimistic is everything. So if all the facts in the world hold, that's like the most optimistic. That's like all the information, it's most likely completely incorrect. Okay, and in the May analysis, most optimistic is the empty set, right? And that's, again, most likely totally wrong. Huh? Right, and then you eventually iterate to get the right answer. So what? Yeah.
So,
But yeah, you go. Oh,
go ahead.
Having a full set in the must point to analysis, what does it mean? Because the pointer can only point to one.
Yeah.
Must point to one particular. It cannot must point to two.
Right, well, so we actually talked about this for constants, too. It's the same thing, where basically it just means that there's an inconsistent state. And it actually really means that it's like not only you know that it points to something, but you can even pick which one it points to. That's one way. The same thing we said that it can be multiple constants. It's like all these constants, you can not only be a constant, but you can pick which constant it is. So for the May point to, the most optimistic is empty set, right? So empty set is basically like it just means that it doesn't point to anything. Okay. It doesn't point to anything.
So if we get that information about a pointer, then what does it mean? Like, was it null? Was it uninitialized? What?
So it probably means that it was either uninitialized or, right, so uninitialized is probably what it would mean.
So the full set includes this 5, right? The most conservative one includes this one, right?
Well, no, I mean, these are just sets. So basically, this is a piece of information. This is the empty set, and this is the full set. The full set just contains, so basically, you look at it, this set has all the all the x arrow, address of y is address of, x, etc., etc. So basically, this is a full, so in a power set lattice, basically every element of the power set lattice is a set.
Including 5.
No.
But the most conservative should include the most optimistic, right? That's why it's the most conservative.
No. So the way our lattice works is that you have a power set lattice where you have top and bottom, and each element is a set, and then they're ordered in a particular way by the subset relation. So So basically, this is going to be a subset of this, and it is.
Right.
Right, but it's a subset. It's not a member of. So this is a subset of this.
Okay.
That's different from being a member of.
Okay.
So this full set is not a set of sets. It's a set of actual facts about the program,
Mhm.
right? And this basically says no facts. This says all the facts that you could ever imagine in the world.
Okay. So the most conservative will have two sets.
Huh?
We'll have two sets, right? Set of all these facts and the set of facts.
No, it'll just have a set of all the facts in the world. This is the empty set. This is the set of no facts in the world.
Okay, we'll discuss it.
Okay, we can talk about it. So let me just say one more time. Think about, we have facts about the program that we can talk about. This is a set of all facts, and this is a set of no facts. This is the empty set is a set of no facts. This is a set of all the facts in the world. Yeah.
Am I right in thinking that, I mean, for starters, topic most conservative, if we ever have that, we could say.
Topic's always most
So that
conservative.
means, like, with that in mind, we're not gonna do any optimization, but for the most part, there's nothing, we can't do any pointer optimization because we don't know anything about it.
Sure, in general.
And then the bottom, if that's what it is at the end of the program, it's like something went wrong, some
Well,
other
not
path-
something wrong, something really weird is going on.
right, some other path might have to clean some
Right.
unreachable code or something, but
Either on reachable or
Right now,
someone that's
it's
like
out.
variable or something weird.
Right
Most
now,
likely, in most cases, you will very rarely encounter bottom at the end of once you reach fixed
so
point.
you
Top
wrong.
Top is top is very feasible to have because when you get to a function call or certain things, you may just give up. There may be certain things, certain features of your program that you just don't know how to handle, and so you'll just return top for those.
Ending with bottom that when if you finished all your passes, whatever order.
You need to either have
if you have bottom, then you have some invalid code, and if you
It's
have
not
top,
invalid code. I mean, I wouldn't say invalid code.
assuming correct passes.
I mean, you can have uninitialized variables in C. So, I mean, it doesn't mean, so uninitialized code will lead to some bottomness, at least some, not total bottomness, but some, so for example, if you analyze this program in C, this is a beautiful program in C, check it out.
What does that say?
Think pointer.
Oh, sorry, I will write it again. This is int star x. This is a program in C. That's the program. Actually, no.
You have to read it or something.
Huh? No, you don't. I mean, that's the program. And return, and this is it. That's it. And you can put this in a C compiler, and it'll compile it, and it'll run. Which basically means your analysis engine needs to, if C compiles it successfully and you get it executable, it means you need to be able to analyze this. This is correct C. So if you run this analysis, basically X will, there's nothing to tell you any information about X. So basically, you will actually get bottom for X. Right? So you should be able to handle that, and that's. Now, it is weird information, because it really represents that X is like uninitialized. It is a weird piece of information. You're right. So bottom is a little bit odd in that respect. So one way to think about bottom is that bottom is this thing that you really initialize things at, and you hope that eventually you're going to basically get out of bottom and actually get to some real result more than just this kind of weird uninitialized thing. Okay. Wait, where were we? Any other questions on this? Keep asking. Yeah.
What is the domain of our set? Is it variables or does it include constants as well? For pointers.
For pointers, it's just variables. But the point is that this idea holds in general. So for example, we can also do this, for example, in our constant propagation example, right? In our constant propagation, we had variables arrow, having constant values. So in that case, it's the same kind of thing. If we do a must, that's a must analysis, right? Because we want to know for sure the constant is that, right? We don't want to know that X may have the value 5, because that doesn't allow us to do any optimizations, right? If we know that it may have the value 5, it means that it may or it may not. So what we want to know is it must have the value 5. And so it's a must analysis, and as a result, what's the most conservative? It's the empty set. the top, basically where you give up on all constants. Then what's optimistic is the full set where you have basically that thing where you have all possible constants, and it's an inconsistent set, because basically at that point it's kind of this unreachable or kind of a little bit of a weird kind of thing. Set that eventually you would hope that as you reach fixed point, you go away from that bottom. Yeah.
And so for this one, int star x, the must point to would be just x? Like,
So-
because there's nothing else.
So, okay, I mean, let's take a look at what happens if we initialize this thing. If we run our analysis, what do we, so, we basically, this actually would give us that we would basically get the, I mean, it depends on what you start off here. So we have some information at the beginning of the program. Well, what are we going to say the information is here? So one approach, so because when we do our analysis, we have to pick what the incoming information is going to be. So what's the incoming information going to be? So one way to put that incoming information is to put it to the most conservative thing, because we just don't know what happens at the beginning, which would be top or must.
Okay.
We can initialize it to this, and then we get nothing. That's one way to do it. There are other ways to do it where basically the only thing you say here is you only state information about global variables, and local variables like X, you basically kind of you separate information. But actually, it all depends on how you initialize your information at the beginning. If you initialize it with the empty set, which is the most conservative thing to initialize it with, you'll get empty set everywhere. Because there's no statement everywhere, so basically you'll know that, that's the information you'll get.
Okay.
Now, if you have some other piece of information like X equals to Y later on, then after this you will get that X points to Y.
Right. So, you said it can only point to, the pointer can only point to variables, but there's all, I'm thinking of like, null may not be variable, or any constant defined by the program, or a specific spot in an array, all these things, like in intermediate representation, you could say, oh, I'm going to create a variable for it, right, and then use it.
So we're talking about only programs that have variables and no dynamic allocation of memory. We'll get to dynamic allocation of memory later. So this is variable.
There's a constant spot.
Yeah, so then it doesn't point to, so if X is 5, then X doesn't point to anything. It doesn't point to any variables.
There is a constant value thought, like
Yeah.
a constant propagation at a thought. X now points to the address of that thought.
What?
Like, I could trick a function to pass that in.
No. I don't, we're computing, okay. When we talk about pointer information, the only kind of pointer information I'm going to talk about is variables pointing to variables. There's no other kind of pointer information. I don't care about variables pointing to constants. I don't care about that. Maybe in C that can happen in some weird way. We're not going to talk about that.
With the exception.
What?
Except for null.
Well, for null, we can no. So in null, what we're doing is right. So we're creating a new special value to handle null. But you don't actually have to. We can also just not have null in our language. You can just say no null in language. You can usually have that, a language that doesn't have null. If it does have null, then you need to introduce that concept. But I think we're getting off track with this. I mean, we're talking about a lot of details of point analysis. The issue here is more the notion that there's basically main information and must information. And they're fundamentally different in the way that they approximate the real answer, which we cannot compute. And we cannot compute the real answer because it's undecidable. To compute the exact set of things that X may point to. That X would actually point to at runtime. So we have these two ways of approximating them. One which is basically saying it's okay to basically overcompute the set of things, and another one which says that it's okay to undercompute the set of things. And so here, what's safe? It's always safe. So is it safe to add information in a main pointer analysis, or is it safe to remove information?
Yes, you can add.
Right, so it's always safe to add. I can always add information. But I can't remove information. Unless I really am really sure that I can remove that piece of information, right? If I'm removing some piece of information, I better be really sure that I can actually, that it's really the case that that thing really never happens at runtime.
Once you lose the fixed point, you do that? Like, we had it before, like, you only go up the ladder.
Right. But my point is that, right, so you would lose your fixed point, and then you can kind of iterate the fixed point again, but the point is that at any point in the middle of my analysis, I can always just add some information, because that's safe. I mean, it's always just safe to kind of, or even at the end of the results, I can do my fixed point, and then let's say I want to add more information. I just decide, you know what, for the heck of it, I'm going to add more information. That's fine to do, and it's not going to break the optimizer, right? Because I'm just adding more information, and it's going to be fine. But I can't remove information. If I remove information from a main point you said, that could actually break the optimization path that goes on later, because it may make the results incorrect. So adding information on a main point, on a main analysis, will still, on a correct set of main analysis, will actually not invalidate the information. It will just kind of add more information, will make it less precise. What about must? So in a must point to analysis, in a must analysis, what happens? It's always safe to remove information. Right? I'm just forgetting facts that I knew. Right? Like I knew this fact, and I just choose to forget it. And it's fine. The optimizer will have less things to do because it won't have as much information, but it's safe. But adding facts to a must once I run my must analysis, if I add more facts to it, I can't do that unless I'm really sure those facts are correct. I can't just go in and just add random facts, right? Because that'll make the optimizer use incorrect information. So do you see how I can remove information, but I can't add it? And with the main analysis, you can always just add more stuff, but you can't remove information. So there's kind of these duals. Yeah.
Maybe you can clarify to me what you mean by safe. So for me, I can understand, yeah, sure, it's always safe to add information because we have the same concept that it points to. But if we remove information, then we have to be sure that what we're removing is safe to do so. So I don't see how it's always safe to remove information.
So, I mean, so the way to think about it is that, think about, you know, something like constant propagation. If I have a whole bunch of facts telling me that X is for sure 5 and Y is for sure 10, then I'm going to have an optimizer that's going to use those facts to do transformations. If I remove those facts, it's just going to prevent the optimizer from doing transformations, but it's safe. It's not going to make the optimizer do incorrect things. Right? You're talking about in terms of the pointer analysis. Is that it? I mean, that's slightly, I think for the pointer analysis, it would require a little bit more thing to actually create an example that will make the optimizer break. It's a lot easier to think about it from the point of view of something like constant propagation. Where in constant propagation, if you have X is mapped to 5, the optimizer is going to replace all X's with 5, right? It'll optimize it. And if you remove that information, it's safe. It means the optimizer does not perform that optimization, and you're still fine. You'll just use X instead of 5. You'll lose optimization opportunities, but you won't actually create incorrect optimization. Does that make sense?
Yeah.
For constant prop. So pointer is a little bit more complicated to actually to come up with an example that really demonstrates that. But I mean, yeah.
We're just talking about optimization and we just don't do something.
Yeah. So okay. So let me give you an example. I mean, for example, if I have okay, you're actually right. So I can easily let's say I have this, and let's say I know for sure that X points to Y. I can replace this by just saying Y equals 5, right? Okay, well, if I delete that fact that X points to 5, then I don't do the optimization. But I'm not gonna do wrong optimization. Whereas if I add a fact, let's say I just add the fact, oh, by the way, Y points to A. Then that's actually really dangerous because then this would be replaced with A is 5, and if that information was wrong, then that'll make the optimizer do incorrect things. So if I add that Y points to 8, I'd better be really sure that it's okay. Like so removing facts, I can just go and remove facts anywhere and the optimizer will still be okay. Or at least not do incorrect things. Yes?
I think the part that might be because even if when you say, the optimizer will not do something incorrect, you mean it will not do something that breaks program, correct?
It will not,
It may fail to optimize, but it will not do something that breaks program.
right, it will not create a program that whose behavior has been changed. Right. And, right, yeah, yes.
So I'm guessing this is an example for math. Can you give a similar example for like main as well?
For a main point information, okay. So here's an example for main. So, let's say that, you know that this is constant pop, and you know that y is 10. Okay? And then here you have, print y. Now, the question is, can I figure out that after this statement y is 10? So let's say that we have some may point to information, okay? So this is may point to information, which tells me that x may point to A and x may point to B. Okay? So basically the way pointer information works is that usually you pre-compute it, so that's some computer information, and then you're doing an analysis that allows us to use that information. Okay? So if I have this points to set, this may points to set, so x may point to A and x may point to B. What does that mean? It does not point to y. Now, notice that basically this was like x may point to A and x may point to B, but now I get some must information that x must not point, it definitely does not point to y. And therefore, I can actually, my optimizer can optimize this to 10, right? Okay. Now,
But it's safe to add information. So in this case, that would mean like, we could add saying x may point to y.
right, so if I, for example, add information like x, so it's definitely safe to add, let's say, x may point to y. I add this information, oh, well, it's always safe. I can just keep on adding. Add whatever information you want. The optimizer will not break your program. It may not do some optimizations, but it's not going to break things. So notice I can add x may point to y, and what's that going to do? Then I'm not going to do this optimization. But notice the other way around. Notice what happens. Let's say the situation was different. Let's say that my analysis really computed this. It really is possible for x to point to y. There's a path in the program where x may point to y. Then my optimizer is not going to do the optimization, which is the right thing to do. Now, if you go in and you say, aha, I'm going to remove this thing, that's bad. You can't just go and willy-nilly remove things, because that will make the optimizer now put 10 here, which is wrong, because actually x in fact may point to y. It really could happen at runtime that x could point to y. So you can't just willy-nilly remove information from a may point analysis. Okay. So finally, let's talk about merge. So when you have a may point to, when you have a may analysis and you have a merge point versus a must, so basically, obviously, one of them is going to be intersection, the other one is going to be union, intuitively, when we're talking about a power cell lattice. So which one is which? Huh? Right, so in the may, basically you count on both sides, it's basically, it's going to be either one of those things, so union it, and the must is, you only say that a fact holds here if it holds both on both sides, right? So you have to be sure that it really, really holds. And the only way you know for sure is if it holds on both sides of the thing. Okay. Cool. So let's talk about common subexpression elimination. So let's do another example where we are basically going to compute some information about first of all, what is common subexpression elimination? Do you guys remember? So common set expression elimination is something where you have, you know, an expression, let's say a plus b, and then later on you use a plus b again, and you want to basically replace this with x because you already have that value stored in x. You want to remove that redundant computation. And so, so what kind of information are we going to compute here? So is it going to be must information or may information? Yeah, so it's must. I mean, we want to know at the later point, we want to know that x definitely is equal to a plus b. We want to know that it must, it's not that it may be equal to a plus b. We want to know that it really is equal to a plus b so we can do the transformation. So a lot of times you decide on may versus must based on the kind of information you need for your optimization. So in terms of the domain, so let me write down, let me just show you what the domain is. So because it's a must analysis, it's actually these, the bottom, top, and the join are basically all based on the previous slide. So the most optimistic information is the full set. The most conservative is the empty set. You just give up on everything. You're like, I don't know. There's no equalities. And the kind of information we'll be computing is basically x or e, where basically this really shows that x is equal to e. What it means is, whenever we compute this at a particular point, it means that the value of x is equal to the value of e, where e is an expression and x is a variable. Right, so we're computing inequalities between variables and expressions. Yes.
So how do you define expression?
So that's a good question. I mean, one way. So they're right. Okay. That's a great question. Let me answer that in a second. Okay. Folks, I have a great question. How do we define expressions? What is this expressions thing? I said here, okay, so what, does anybody have any ideas on how to define, so what is this set of expressions?
Something that must be computed or interpreted or...
Right, so the simplest thing is to say the expressions in the program, that occur in the program, right? I mean, basically all the expressions in the program. You just take your program, compute all the expressions there. And in most cases, that'll probably be enough, because what we're doing is we're taking like a plus b expression here, and then it's recomputed down here, right? So it's two expressions, both of which happen in the program. So that's kind of the simplest way to do it. There are more sophisticated versions of this, where you can actually take a set of all possible expressions, and you can actually be clever about how you combine them, and you can make better flow functions. But for now, we could just say it's a set of expressions in the program. The nice thing about that is that it also makes the lattice finite. Like everything's finite, right? You guarantee termination because you're not building expressions on the fly. It's only the expressions that exist in the program. Yes.
To be clear, we're not talking about where a plus, like x equals a. We do x equals a plus b plus c.
Whoa, what's even that? I never heard of that. I don't know what you're talking about. What?
Expression.
We don't handle such statements.
Really?
We don't have such statements in our language.
Oh, you use like binary numbers. Okay.
Yeah. So we can, if you want. So if you want to design your language, your intermediate language, remember this is our intermediate language, it's not the source language. If you want to design your intermediate language to have 3 operators like that, then it means that you have to also write flow, every time you write flow functions, you're going to also have to define flow functions on all of these other operators. And it gets pretty nasty, right? Because it's like now you have multiplication, you have addition, what about multiplication and addition? Right, so all of a sudden it gets much more, so it's much easier to say we're only going to have binary operators or unary operators. And then you can basically, you analyze programs in that way. Now, you're right that even though your original program may not have that, you could possibly compute information that recovers that stuff. Right, so for example, let's say you have, something like A is equal to B plus C, and then you have D is equal to A plus,
F.
C again. Or would you say F?
Whatever.
F is good. I like F. Then you could basically compute maybe you want to know that B is equal to A plus B plus C, right?
Well, where I was going to go with it was, I guess a better example would be like print AB, and then later on print AB again, where I didn't use a variable to store this. then we're not gonna cover it here, like, same expression, but we didn't create a temporary variable, so we don't.
Sure, sure. Now, with all of these things, basically, you can like, there's this wide spectrum where you can be very conservative and you can also try to be more and more precise. There's many, many different versions of this. We'll just try to keep all the expressions to be the expressions in our program just to start off with, just to kind of get a feel for what's going on. Okay. How about you guys try to write the flow function for these things?
I have a question.
Yes.
So does expression, for example, is a plus b plus c? So the expression you could mean a plus b and b plus c would be two expressions, or would you consider a plus b plus c as one?
So I will only consider expressions that are in the original program, and in the original program we only have binary expressions. So basically you will only have expressions in the form a plus b. Or you can also have expressions in the form b plus c. You will not have a plus b plus c. You can design analyses. Once we define this, you can always add bells and whistles that make your lattice more complex. These are just, I mean, when you do this to reality, you can actually have much more complicated lattices that do these kinds of things. But now you get into termination issues, and you have to be a lot more careful with how you actually, because now you're going to be building possibly, expressions on the fly, so you have to be a little more careful about how you do things.
What I mean is, plus is still a binary operator.
Yeah.
But the parse tree is like a and then b plus c. So it depends on the parse tree how your expression is actually.
Right, and I'm going to say in our language we only have parse trees that have like this.
Or unary.
Where you have only two operators. Now, in reality, if you have other things, then the simplest way is to decompose them into this stuff so that you have your flow function, you can run it in this way. Otherwise, you basically have to write a flow function for every single one of these parse trees, which you can do, but it's just much more complicated. Okay, how about you guys try to do this one? So remember, a lot of times the way these things work is this is a set of things, so a lot of times the way you do things, you have to figure out what you need to remove, and then you have to figure out what you need to add. Right, so you're going to take the input set that comes in here, you're going to remove a whole bunch of things and add a whole bunch of things. Yeah. Oh, wait. Are you going to give the answer? No, wait. No, I hold on. I want you guys to try it out. Like, literally try it out. Like, everybody, this is a good thing. The midterm's coming up. You guys should be like, hello, like, this is like for the midterm, because in the midterm, you can be doing exactly this thing. So, just like, get some practice. And if you figure it out in your head, that's great, too. But I'm just saying, let's let everybody try it out, just to give you some practice. Okay. So I've written my answers here. People look puzzled. You look like we're frowning. Yes.
Why is the variable or expression?
So you're saying.
What was your question?
Wait. Hold on. I'm trying to figure out what the question was. I think so. What you're saying, you're asking, should I not look at
Y and Z inside of it?
so and if Y and Z, so if Y is mapped to expression, then you're saying that. And but the idea, so, okay. Hold on a second. So, let's first try to understand, there's two kinds of objections that one can have about a flow function. There's precision issues and correctness issues. Correctness issues are things where you actually literally will compute information that's just wrong. And then there's precision issues, which is you're not computing enough, you're not computing as much information as you could, right? At least in this setup, that's how it is because it's a must analysis. So are you mentioning, is it a precision issue or a correctness issue? Okay, precision. So let's put that on pause for just a second. We'll talk about that, but let's first see, so, are we happy, at least, the thing is this, precision, I can always make things more precise, but let's first talk about correctness. Is this a correct thing? Yes.
I don't know what you mean by E.
Wait, what? Is this one? Let's talk about the top one first. Let me just deal with the top one first. We'll get to the bottom one in a second. So let's take a look. So what does this top one do? It just covers all information about x, and then it basically says that x is equal to y off z. That seems very intuitive, right?
Is that, right? It's not the precision.
What?
That is the correctness problem you mentioned. You know, if y or z is not constant or it's not assigned to something, then what will be the y of z? Do we define the operation, for example, operation add or something?
No, I mean, you can have, it doesn't mean that if y is not mapped to anything that it doesn't have a value. So remember, this is a must analysis, so at a merge point you do intersection. So y may be just defined as two different things on the two sides of an if, and then when you merge them, you get no information. So actually, that doesn't mean that y is not a correct value. It just means that we don't have any information about y, about any, so that's actually okay.
If we don't have any information about y, then we don't have any about it. This one doesn't add anything.
Wait, hold on. Yeah. Yeah, so let me just give you an example. Suppose I have a statement like this. It doesn't matter what B and C are, what values. I know that after this statement, A is equal to B plus C. That's what this is really saying here, right? And it doesn't matter. So this is, so in that sense, this thing I think really was a precision issue. But yes, did you have a comment?
Yeah, I think that the original question that kicked us off about looking up the expressions, it depends on whether or not your expressions are multi-array. Because that's a binary expression, that's definitely a valid thing in whatever language we have. But if you look up the expression with y off z and just kind of stick them in there,
Right.
when those are expanded, those will end up as like a 4-array
Right.
sequence of ops.
Right. But that's exactly, and that's very complicated. So let's not talk about that. I mean that
That would actually be incorrect, right?
Well, it's not accepted by that.
Yeah, I mean, it's not even part of our domain. It's actually very right. It's not part of our domain. It's very right. But hold on. This is like, I feel like we're this is like, I don't. This is like, you know, it's like there's a tornado coming and the whole building's about to fall over, and we're worrying about like, oh, the color of this chair, I don't like it. And I was like, there's some stuff that is fundamentally, completely broken about this. This is like so bad. Like let's first talk about, this is like totally wrong. Okay, it's fundamentally completely broken. So let's just first try to understand why this thing is so broken. It's ridiculous. It's like we should, yeah. So there's some really bad things going on here. Like this thing is really blatantly incorrect. So let's try to understand what is blatantly incorrect here.
For the first one or the second one?
The first one. So let me like, so this is why. So let me just say, the fact that you're not seeing this right away is an indication that flow functions are actually really hard to write. It's really not easy. And you have to really think very carefully about all the possible cases and everything that's going on. Yeah.
Well, I was thinking about the previous example, which looks exactly the same as this one, but you write in a different format, which is x will point to n, while y will point to n1 and z point to n2, which both belongs to the E.
Okay.
Yeah. I think this is just the same as the previous example.
Well,
But why just why did you just write it in a totally different way?
Oh, this
Like
thing?
before, yeah.
This thing?
Yeah.
So this is a very different analysis. We never done this analysis before. This is basically, we never done this actually flow function before, right? I mean, previously, we never done, this is a totally different flow function and a different analysis. Previously, it was actually very different. It was actually, we were computing constantness information. We never had x equal to an expression. We always had x, we always mapped x to constants. And we only computed that constant if we actually could figure it out. Here we're actually mapping x to an actual expression. So what we would do is, for example, we were basically, if we had this statement, we would compute the information at a, let me write it differently. I'm going to say a is equal to b plus c. Actually, no, I'm just going to say a arrow b plus c. Yes?
Is your concern correctness about the flow function or correctness about like does it fit into our?
Correctness about the flow function. There's a very simple program that I can write where this, okay, well, first of all, what does this thing do? Let's focus on this.
Takes out everything.
Well, it removes everything where x appears on the left-hand side of the arrow. Okay. Okay.
If it's x equal to x plus 5 or something?
Okay, so wait, okay, that's a separate, okay, so you're asking, so let's take it one step at a time. So, you're saying x equal to, so, strictly speaking, this doesn't fit our syntax because both of these have to be variables. But let's just say, let's do this. So what is your analysis going to compute on this? What is this flow function going to compute on this? So actually, let me actually do it. A is equal to a plus b, and I'm going to do it this way because just to kind of not get confused with these x's. Okay, this x and this y, these are the patterns. Does that statement does it match this pattern? Yes. What would our flow function do? It would compute the information that a is equal to a plus b.
Technically, our expression has three different variables. So
What?
x, y, and z are three different. We could make it a little bit more strict.
Yeah, but there's nothing here that says that these things should be different.
I think that we can change the flow function.
What? Well, we could change the flow function, but currently the way it's expressed, right, this is a pattern. This pattern matches that statement. I mean, if you write something of this kind, yeah, I mean, this will actually apply, and you'll conclude the information that a is equal to a plus b, which is totally wrong, right? I mean, the interpretation of this would be that a is equal to a plus b, which is completely wrong. It doesn't, and really, what the reason why we're doing this kind of stuff is so later on, if you see a plus b, you can replace it with whatever you had here. So if you had this kind of information, what you would do is later on you have an a plus b, which your optimizer would transform to a, which is wrong, right? Because a doesn't have the value of a plus b anymore because a got changed. Okay? So these are the kind of subtleties that you need to really think through when you're doing all these things. It's certainly possible for these variables to be the same thing. So what we want to say is that why, but wait, so hold on. So what about this? So that's okay, right? So what we want, so y and z can be the same. But x and y have to be different and x and z have to be different. Right? So we have to say, this is a little bit, I mean, this is like, you have to be careful here because otherwise you do this in a real thing, you're actually going to break the compiler, you're going to break programs. Okay, so that's the first step. So here we have to really be careful how we add this information. Okay, now, what about the other case? So what this is saying here is that we're removing everything where x is on the left-hand side. Right? How is that? Okay, so what's an example where that would be, let's figure out an example where this flow function, so wait. So okay, we made this better. So now let's figure out an example where this flow function would actually break. So we fixed this thing, but this thing is wrong too, actually. So what would be an example where removing everything on the left-hand side is not right?
Didn't we say we can remove things really? So isn't this a case where we can just go ahead and remove stuff?
Well, right, that's a good question. Hold on a second. So, so this is a must. So this is a must analysis. Okay, this is a very good question. Let's think about this very carefully. So here you're removing. When you run this statement, there's a whole bunch of information that's going to get invalidated. Okay. If you forget to invalidate some information, then you will get information that's actually invalid afterwards. And that's actually wrong. So the place where you can actually, because the must analysis, the place that you can actually delete things is here. You can basically just say, you know what, I'm going to forget. In fact, you can just remove this whole thing. And your analysis would still be correct. You would just not be adding information. That would be conservative. You would be adding less things. But if you don't remove enough stuff, really, by removing stuff from this set, because it's in the negative position, you're actually accidentally adding stuff to the output set. Okay, so what's an example where this would actually break? So when you're going to see this, you're going to be like, no, I'm not worried about that. That's. I mean, we could just. I mean, it's much more fundamental than that. So let's just see. Let's say we have A is B plus C. That's this statement, right? So what is our flow function going to compute here? Okay, and that seems okay, right? So far, so good. And then what do we do? So let's say I do A is equal to, let's say, D plus E. What is our flow function going to do? It's going to remove the information about A, and it's going to add that A goes to D plus E, right? Okay? So far, so good. That's not a problem yet. Okay. That's fine. So what do I have to do? B gets what? 5? Nah, that's not a great example because it's not going to be this flow function. That's going to be a separate flow function. I want to just do it in terms of this flow function because we haven't seen any other statements. For now, our only statements in our language is this, right? We haven't seen. So B is equal to what? E plus F. So what is your flow function going to do? It's going to remove everything where B is on the left-hand side. There's nothing to remove. So, and then it'll add the information at B. So basically, it'll basically compute this. And then it'll compute that B goes to E plus F. Right? Are you guys seeing this now?
So how do we know?
Wait, are you guys seeing it? So you're not seeing it?
No, yeah.
Wait, hold on. So wait. So we just figured out that after this statement, A is equal to B plus C. So what that means is if later on I see B plus C, I'm going to replace that with A. But that's wrong because B was actually modified in between. I can't, this B plus C is not the same as the value in A anymore because B got modified, right? So this B being modified actually should, so we shouldn't just look for B on the left-hand side of the arrow, we should look for B on the right-hand side too, right? Because any change to B will invalidate any fact where we have that involves that variable, right? Because we just don't know anymore that it's equal, right? Here, basically, we knew that A was equal. Essentially, what we knew was this: A is equal to B plus C. And because we modified B, we don't know anymore that A is equal to B plus C. So we should delete that information. So in fact, we should basically also remove anything where basically X is on the right-hand side. Okay, you guys see the? So you guys see why, to me, like this was the tornado that was like killing us. I mean, this is completely incorrect, right? We wrote a function. The original flow function looks so simple and clear. Like, well, obviously it's correct, but actually these subtleties really come back to bite you. And the flow function was just completely incorrect. You could have really simple programs, not even involving loops, right? Really straight line code, where we would basically be computing information that would lead to incorrect optimizations that would change the behavior of the program. So what does this mean? This should basically make you think 10 times when you're actually writing these flow functions down. Try them on examples. Try all these various combinations. Ask yourself, what is the thing on the right? Is the same, like, does it all make sense? Like, you know, try to think about all these cases to make sure that you actually are handling all the corner cases. Yes.
So for this analysis, when we go to the next one, though, we have to include all those types also, right? If we have,
When we do what?
for example,
When we do this one?
or put another way, both these flow functions would be part of the same optimizing path.
Right. Well, it's the same different analysis. We haven't even written this flow function yet. We were just talking about.
saying that the fact that there's other syntax exists, the bottom of the syntax is part of the language, we have to include that in the top flow function as well.
No.
Because
This flow function only handles information that goes in,
what if we, in the example we just had, for example, where we had to get rid of it where X was also on the right side.
right.
But we only got rid of it where X is on the right side, either the Y or the Z variable. What if it's in the bottom example?
But I'm not going to store, so what I'm going to do here is I'm not going to store that, if I have this, I'm not going to store that A goes to B, because that's actually kind of boring. What I'm actually going to store is whatever B would point to, I'm going to make A point to that. So whatever information I knew about B.
The other way.
Exactly. So, but yeah, you're right that,
Oh, because we can't do variable to variable anywhere.
right, I mean, so you're right that in some sense, all your flow functions together define a set of facts that can come up. But the point is these issues were in isolation just related to this flow function, these correctness issues. But the bottom line is this, what you have to do is you have to remove any fact involving X in this setup. Any fact involving X, whether X is on the left-hand side of the arrow, on the right-hand side of the arrow, just obliterate everything related to X. It's not just X on the left-hand side. It's X anywhere in your fact. You should remove it. Okay, we have one more minute. So what about this function? This actually, so here what we're doing is removing everything about X, and then, oh wait, so we should do the same thing here, right? Wait, so you have a question?
So this is like adding a sub-expression, right? There was no expression, but it added it instead of a...
Wait, which one? This one? Or?
Right.
No, I mean, it's only adding in its Y, if you knew information about Y.
Right, so if y was a plus b, then you would put x as a plus b also.
Yeah, which is true. I mean, X is going to be, because X and Y are going to be equal to this. So if you knew that Y is equal to A plus B, then basically you're going to also know that X is the same thing.
So the next time you encounter a plus b, you can replace it with x or y.
Exactly. And the part of the reason why you may want to do that is because you're actually going to get merges later on. So some of those X and Y's may actually get obliterated because they may not be available on both paths. Down here, again, we have to be careful with this because this actually, if we have to do the same kind of trick there. We should just remove any fact that involves X because we're just obliterating X. so we don't know anything about it. Okay, the one thing so there's two lessons here. One is, flow functions can be tricky. Think 3 times when you're doing your midterm. But more broadly, because it's not all about the midterm, more broadly, correctness of compilers is actually a really big issue. It's actually really subtle, and you can actually, and this is just for a simple language. Imagine when you have like, you know, lots and lots of possible different flow functions you're writing, and you're doing complicated analyses involving pointers. It can be really, really hard to make sure that your things are correct. And in fact, we have a whole bunch of research that we actually do on compiler correctness, where we actually develop techniques for coming up with ways of verifying that your compiler does indeed, you know, it does actually transform the program in a way that doesn't change its behavior. And we'll do some readings later on in the quarter where actually you'll read some blog posts where you can see how horrible compilers are. I mean, you can like find bugs in up-to-date GCC compiler. I mean, you can just like, if there's so many, you can like literally find like 3-line programs that your GCC compiler is completely correctly, you know, optimizing correctly. It's actually pretty astounding how buggy compilers really are in practice. Okay. So what are we doing?
So that second part of the second one is correct?
This part, yes, I think this seems correct. Basically, this is saying that whatever Y information I had about Y being equal to some expression, now X is also going to have that information. Yeah. Now, let's talk about, next time we'll talk about the issue, so there's this other issue, which is that you can have these things where what if Y and Z point to these other expressions? What if you actually built these more complicated things and propagated them? You could actually possibly do that, but we're not doing it here. And you could create an analysis that more precisely do that. Yeah?
Can we write, in the second function, can we write x points to y directly?
Yeah, you could do that too. That would also be another way to do it. You could basically just, yeah, you could just say that X just points to Y, but that's not that useful. Because it's like, yeah, so, that's not that useful. We'll talk about that next time. How about you ask the question on Thursday? Again, so we'll just talk about it. What?
The second one's correct.
If you update this to be this. Right, you need to basically delete all information about X, not just on the left, but also when X appears on the right.
Do we have to say Y not equal to X? So that
That's
one?
fine. I mean, if Y is equal to X, then it's okay. It's a self-assignment. It actually kind of works out. So you have to think about all these things. That's true. But the point in this case, it actually works out.
Okay.
Okay. All right. See you guys on Thursday.